dimensions percent change. And I suppose the best way to deal with this is actually give you an example problem that you can write down and we'll talk about it. For example, here we go, let me find them here. One square is 50% larger than another square. One square is 50% larger than another square. What does that mean to you or me? I don't know. We'll talk about it in a second. Let's look at the questions they're going to ask us. The perimeter of the larger square is what percent the perimeter of the smaller square? Perimeter of larger is what percent of the smaller? Is what percent of, this was supposed to be the word of the smaller. That's question number one. Question number two is the area of the larger is what percent of the smaller? Area of larger is what percent of the smaller? And last but not least, the last question could possibly be, it's Lucas back there talking. That's who it is. Sage, why didn't you tell me that? Did you hear that whispering back there? Oh, I guess that's the two questions we're going to answer right there. Let me see if I can blow this up a little bit. Actually, I'm going to shrink some of it down and blow it up. If all goes as planned. Uh-oh, there's some of it, but that's okay. Okay. Now, here is the first thing you must understand, okay? You need to sketch this out. You must do the drawings. Now, here's the beautiful thing. Here is the beautiful thing. How big of a square am I going to draw? For example, what are the dimensions of the smaller square? Schwartz? Schwartz doesn't know. Would somebody tell me the dimensions of the smaller square? Price? You do. Thank you. We have learned something here. They don't tell you. They just say you're taking one square and making another square 50% bigger. So they don't give you any dimensions. The beauty of this is you get to pick whatever dimensions you want, and you might as well pick the easiest ones humanly possible, because it'll work no matter what dimensions you put. So let's pretend, or say we have a square here, a smaller square. Okay. Now, if in math, are you okay?
No, it's not.
Schwartz, I've got just the thing for you, sir. Okay, so this would be my suggestion. If you're not given the dimensions, what number is pretty much one of the easiest numbers to work with? Well, if you deal with 1 though, and you're making something 50% bigger, you're probably going to have to deal with decimals there. I would pick 2. No, I'd pick 10. Well, okay, let's go with 2 because so many people said 2. It's a square, so you know that these sides are both 2, correct? Now, the next square, the bigger square, is 50% bigger. Okay, 50% bigger means that you take 50% of it and add it to it. For example, if if you weighed 50% more next year than you do this year, that means you gained half your body weight and added it to it. If you weighed 100 pounds this year, you're gonna weigh 150 pounds next year because you added 50%. So if I have two, what's 50% of two? What's half of two? 1. So you take 2 plus 1, your new square is 3 and 3. Understand that? If it would have been a 100% increase, it would be 4 and 4. 200% would be 6 and 6. Okay, so now you've got your two squares that you're going to work with here. Now we're looking for both the perimeters and the area, so you're going to do that. Let's find the perimeter and the area of both of them. It's not going to be very hard. What's the perimeter of this small one? 8. What's the area of the small one? 4. What's the perimeter of the big one?
12.
12 all the way around. And the area of the big one? 9. Okay, now, here's where it gets a little touch and go here. Okay, they want to know the perimeter of the large one is what percent of the small one. Okay, the perimeter of the large one is what percent of the small one. Now, if you look at this, there's a couple different ways we could do it. We could probably draw a box. Let's see what happens when we draw a box. Because we know our actual numbers. We know all the numbers we need. We need to figure out the percents. Okay? So let's look at this. First of all, what our original one was the small one. Okay, we added what percent to it?
50.
Well, let's not do it that way. Let's do it this way first. What was our actual one? Our original one, the perimeter was 8, right? What do you add to 8 to get to 12?
4.
You get 4. Okay? We know our original percent is 100%, right? And we want to know the percent that the big one was. So this is what we don't know. Okay? That is what we don't know. So if you're going to do this out in fraction form, it is 100 over what number is equal to 8 over 12. We've done this, correct? So what's my best way to go about doing this one? Reduce it to what? 4 over 6. Can we do that? 4 times what is 100? So what's 6 times 25? 150, right? So the answer to letter A is 150%. Which makes sense because I added 50%, right? 100% plus the 50%. But that kind of falls apart a little bit when we do the area, because the area is going to be a little different here. Take a look at the area. It's really the same box with just different numbers in there. Our original one and our final one. What were our numbers here? It went from area of the small one was 4, correct? And the area of the big one is, thank you for 9. So it went up how many? 5. Okay, I know the original one is my 100%, so now I need to know what my final one is. So there, I don't need the middle box because it didn't ask you for that. It didn't ask you by what percent it increased there. So what do you get if you take, let's just do it, 100 over n equals 4 over 9. What times 4 is 100? 25. Now what do you get if you take 9? If you have 9 quarters, how much is that? 225%. So the area went up 220. The area of the new one is 225% bigger. Okay. Now why, ladies and gentlemen, is the perimeter 150% bigger, but the area is 225%? Can anybody give me the answer to that question? It's the same square, went up the same amount. Why is the area so much bigger percentage-wise than the perimeter would be? And again, it's because of what simple little fact? Rockwell?
4 sides went up.
Yeah, but the 4 sides went up on the perimeter too. We talked about this before. The difference is, in this case, you are multiplying 2 dimensions that both were increased by 50%. Okay? both of those were increased by 50%. So it's really, well, we won't go there. Okay, you're multiplying, this is just adding, so it's one, this is really a one-dimensional figure. This one is two dimensionals. You're actually multiplying two things, like it like doubled itself twice, is kind of what happened there. Okay, it is, yeah. Do we do that right? Yes. I think we got that right. So with that being said, let's look at another one that maybe isn't quite so happy or splendiferous here, right out of the book here. How about this one? The towel shrunk 10%. The towel shrunk. The towel shrunk 10%. Okay. The area of the towel was reduced by what percent? Area was reduced by what percent? Oh, spelled that wrong. How's that air freshener working for you, Jeremy? You know, if you wave it around a little bit, it kind of wafts through the air. You probably stick your finger in it and smear it all over your face. Okay, so here it is. Let's just answer that question there. So what's the first thing I'm going to do? You're going to sketch it out. So you're starting off with the towel. Okay, but this towel got smaller. Okay, it shrunk by 10%. That means it got smaller by 10%. Again, what are the dimensions of the towel? They're not given, so you get to pick. So think about this. Pick a number that it's easy to find 10% of and work with. Jeremy, I like 10. And it doesn't matter. It could be a square towel. I guess I should have drawn it as a square because a square is easy to work with. It did say it was a rectangular towel, so let's pretend it's a square, and it is 10 inches by 10 inches. If a towel is shrunk by 10%, what would the new dimension be? If you have 10% and it shrinks by 10%, okay, that means it went down 10%. Nathaniel?
9 inches.
Right, it's now 9 inches by 9 inches. Because you take 10% of 10, which is 1, take 1 away from that, it is now 9 inches. And we're only talking about the area now, so let's write down, what is the area of the original? 100, correct? What's the area of the new one?
81.
81 inches. Now, if I do my little box, let's see what happens here. This time, I know my numbers. I guess I don't know my percent here. Our original tower, and then it was reduced. This is the reduction right here. That's the number we're actually going to be looking for. And here's our final. Okay, it started out being what? 100 centimeters or inches squared. Ended up being 81. Okay. How much did it go down then? It went down 19. So the original was 100%. Oh, I like where this is going. And I want to know, it asked me how much it was reduced by. It wants this one. It doesn't say the final towel was what percent. It says how much was it reduced by. So if you stick those numbers in there, does math get any easier than this? 100 over what number equals 100 over 19? 100 times what is 100?
1.
So 19 times 1 is 19. So the answer is it was shrunk by 19%. The new area was 19% smaller than the other area. Isn't that exciting? Should we try one more? Oh no, here's one. We'll do one more, because the practice problem gives us one more. It says, last problem here. If the dimensions of a cube are increased by 100%, if the dimensions of a cube are increased by 100%, the question is, by what percent is the volume increased? By what percent is the volume increased? Anybody care to take a number, guess at this? Somebody says 50?
Yes.
It'll do 10.
No, I'm just asking, what do you think the answer is, just out of curiosity?
50.
Huh? 300% bigger, 200% bigger. Well,
What did you say, 600?
here we go, here's my cube. This one should be simple, again, 2. Here's my cube, my original starting cube. It doesn't say what dimension, but we know we're increasing it by 100%, so you're actually in essence doubling it. What dimension do you want to go with? What? I'm gonna go first cube be 10 by 10 by 10, and the second one 20 by 20 by 20.
Okay, we'll do
5.
Or you could do 1 by 1 by 1 and 2 by 2 by 2.
Okay,
Yeah.
five.
Or you could do 2 by 2 by 2 and 4 by 4 by 4.
No, 1 by 1 by 1 by 2 by 2.
No, well, let's do 1 by 1 by 1. 1 by 1 and by 1. The new cube increased by 100% means that you're doubling it, you're increasing it. 100% of it is 1, so you add 1. So this is now a 2 by 2 by 2 cube. And this time we're talking about volume, and you know volume is length times width times height. So the volume of the small cube is 1. The volume of the bigger cube is 2 times 2 times 2, which is 8. Now let's look at the box we can generate with these lovely, lovely figures. Alright, our actual numbers we know. The original one was the small one. The final one was the big one. And this is by how much the increase was. So it started out being 1, ended up being 8, for an increase of 7. Our original cube is 100. What percent is the volume increase? So they're asking for this. What was the percent increase? Alright, well you could probably do it without us writing the thing. If you were to go from 1 to 100, you multiply by 100. So 7 times 100 is 700. This cube increased by 700%. Which means the final cube is actually 800% of the original one. That's what would go here. The final cube is 800% of the original one, but it was an increase of 700%. Gosh, I hope that's right. Look at it, I got it. I got all 3 problems right today. But again, anytime you're given this, sketch out the problem and pick easy numbers to work with. Write your box and see what you can come up with. Okay, this isn't, you know, it's just complicated more in the wording of it than it is in the actual doing of it for anybody. Won't matter, you'll get the same exact answer. Same exact answer. You can do, and that's why the beauty of it, you can use anything. And you'll get any numbers, as long as you double them, you'll get the same. The answers will fall right in the